Good afternoon, everyone. So my talk today is a little bit different from what we were listening to until today, but I just going to start talking about one thing is that I think the sixth event was called Amazonian Workshop on Black Holes, and all the previous ones were also called this way, but a lot of people in presenting were talking about de Sitter space-time and everything. So I think this is my first one again, and I'm finally talking about black holes, but now the workshop is changed his name. So yeah. So we are going to talk about quantum states for charged scalar fields in Reissner-Nordström space-time. And this is a work done in collaboration with some people, so Visakan Balakumar and Elizabeth Winstanley from Sheffield and Professor Crispino here and myself. And so those are two publications related to this work, so of Physics Letters B, and recently another one that's going to appear in Physical Review D if we are finished the proofs very soon. So a little introduction. So we know that black holes are weird objects, right? But they also seem to exist in nature, and also they gave us a lot of insights about a lot of seemingly unrelated topics, so thermodynamics, particle physics, string theory, and also a lot of interesting things about quantum field theory, for instance, Hawking radiation, and the fact that the particle concept is observer dependent, right? So it's the Unruh effect. And so if we have the Schwarzschild solution, which the solution of a static black hole with no charges, we can basically, you can define quantum states with several desirable properties in a more or less straightforward way. But what can we say about the quantum states of, for instance, a scalar field in other solutions? So the rotating solution and the charged, the Reissner-Nordström solution. So we are going to start with just one slide about canonical quantization, and we are using a model of a scalar field, right? And it's basically the simplest model possible, and of course you can extend this to other fields, but with some problems like gauge invariance and other things. But the main thing is that you have to expand the field in a set of operators. They have this collection of sets which we call quantum numbers, and those of course might be discrete or continue. For instance, if you have the frequency of the field, which is usually a continuous variable, so when you expand the quantum field, so now this field here is an operator in a Hilbert space. You have two operators, or a particle creation operator and a particle annihilation operator, and they obey some commutation relations, which are those here. But this is basically related to the fact that you want the field and the momentum of the field to commute in basically like the same type of thing that you do for X and P in quantum mechanics, right? So the position and the momentum of one particle. And you can now define a vacuum state, which is basically the state that is annihilated by all the annihilation operators for all the quantum numbers that you have. And this is basically would be the end of the story if it wasn't for this functions here, which are what we call positive frequency modes. And so depending on the classical space-time you will have a different notion of what is called positive frequency. And this will influence the choice of a vacuum, because ultimately these A operators are connected to these phi plus functions. And so this will be a problem usually, as we will see in the next slides. So I'll just add that usually what we talk about positive frequency is a field that behaves like the exponential of I to the minus I omega, and this omega is a positive thing. And we will see that this is basically related to so this omega, how you define it, is basically related to what you call time in your expansion. So for states in Schwarzschild spacetime, so the simplest case, so this is the Penrose diagram of Schwarzschild spacetime, and you can have some set of modes which we call in modes. So they come from the future, the past no infinity. They scatter in the space-time. A part goes to the horizon, which is this height plus here, and another part goes to future no infinity. So those are the in modes. And you can also have the up modes. So basically we call them up because it goes up from the black hole. You have some modes coming out of the horizon, and a part gets scattered back to the black hole, and another part goes to infinity. And so with those sets of modes, you can basically put them in the expansion of the quantum field, and you have a quantum state, right? Because you can define a quantum state, the vacuum, by the one that the vacuum, the state that is annihilated by all the A operators in this expansion. But the problem is that in Schwarzschild case, if you do that for the in and up mode set, you get what we call the Bowler state. And so those are, as I said, modes that are positive frequency with respect to the usual Schwarzschild time, so this time coordinate here. And you get something that you don't have any fluxes at all the bound, the future and past no infinity. So the state is as empty as possible at infinity, but you get almost all of your observables, your quantum expectation values are divergent at both horizons. So that's a problem, and you can do better than that, and you define the unruled state. So in the unruled state, you basically you have a thermal flux at future no infinity, right? And it's the Hawking radiation, and you get a better, a better behaved quantum state because you only have divergence on the past horizon. And of course, this divergency is not doesn't really matter, because if you look at, for instance, the space-time of a black hole that's formed by gravitational collapse, you don't have the past horizon, because this Penrose diagram is from what we call an eternal black hole. So you have the past and the future horizon. And this state is regular outside and inside the black hole. But you can also do better than that, because usually the unruled state is what you would use in a physical situation. But what we call the HHawkinslike state is a better, much well-behaved state. And And the price you pay for that is you have both, you have flux from, sorry, so you would think that you would have a flux of particles going inside the horizon and in outside to future no infinity, but actually you don't have any thermal fluxes, and you have an equilibrium state. And that is because it's regular everywhere, and that is because it represents an eternal black hole in thermal equilibrium with our heat bath. So it's a kind of weird space, weird state, because it's as if the black hole is emitting radiation, but it's thermalizing with the radiation outside the space, the black hole, and it's in thermal equilibrium, so it doesn't, its temperature doesn't, it's a constant everywhere. So, but this HHawkinslike state is very useful to do calculations because it's regular everywhere. And I can add that the way that you build this HHawkinslike state is you build modes that are positive frequency with respect to what we call Kruskal time, and you have things like that. So back to the unruled state, if we look at the modes that you use to define the unruled state, so this is important for what we are going to do next, is you define, you don't change the in modes. So you use the same modes that comes from past no infinity, but you define new up modes that are defined with positive frequency with respect to Kruskal time. So you mix what you've seen in the HHawkinslike state with what you see in the Bowler state, and you get used two new modes. You use the old modes, the old in modes, and a new set of up modes. And so for Reissner-Nordström black hole, it's a little bit trickier than that, because so this the metric of Reissner-Nordström black hole. We know that's the space-time of a black hole with a mass and an electric charge, and we are going to look at the charge scalar field equation in this with a complex scalar field, and this space-time includes a radial electric field, which is basically from the charge in the black hole, right? And if you use separation of variables in this phi field here, you get a Schrödinger-like equation for the radial part. And the important property is that the potential that you have is something like that. So at near infinity, the potential is basically just omega squared, and at near the horizon, the potential is this term here. So what we call omega tilde squared, which is basically omega minus q over r plus, which is the radius of the event horizon. And as I said, why it's more difficult to build quantum states in Reissner-Nordström is related to what we call superradiance. So this the amplifications of modes that you throw at the black hole, and you can get some things that are amplified. Some modes are amplified, depends on the frequency of the mode, and the condition is this one here, which the omega is smaller than this factor here. And this is, of course, related to what happens in Kerr space-time, which you have something that's related to the quantum number m of the mode and the angular velocity of the horizon. And there is a quantum version of that, which is what we call For Kerr spacetime, it's the Unruh-Starobinsky effect. So basically, what happens in that is you have a quantum field that is coupled to the classical background spacetime by minimal coupling, say, and the quantum field has an spontaneous emission of particles, and those particles happens, the frequency of those modes associated to the particles happen to be in the superradiance interval. And for the Kerr spacetime, this is known as the Starobinsky Unruh radiation. I don't think if there is a name for the equivalent thing that happens in the charged case, but it's probably really, if we would name it, it would be something like the Gibbons effect or something. And so what happens is that by spontaneous emission of particles, the black hole, for instance, if it's a Kerr black hole, it loses angular momentum spontaneously by emission. And if it's in the charged case, the black hole actually loses charge. And so this is the Penrose diagram of the Reissner-Nordström black hole spacetime. And so we can do the same as we did in the Schwarzschild case. You have in modes which are positive frequency for omega greater than 0. But for the up modes, therein lies the problem, is that you have positive frequency for omega tilde greater than 0. So, and this is very important because what the consequence of this is that we have what the analog of the Bowler state in the Reissner-Nordström case, what we call the Pass-Bowler state, and it has the property of divergency at the horizons, but you also have a superradiant flux at future no infinity. So instead of having a state that is as empty as possible at future no infinity, you get this superradiant flux of particles due to the spontaneous emission. And so one can ask the question of, is there a true Bowler-like state? So can we construct a quantum state that has the property of being as empty as possible at both infinities? So both future and past no infinity. So in passing, we also have the future Bowler state that you can similarly define it, and you get the flux in the past no infinity. But it's basically the time reversal variant of the past Bowler state. And it appears you can do this in Reissner-Nordström, which basically what you do is we have this equation here on top is basically the prototypical thing that you get for an observable in this Bowler-like state. And so this O is the particular operator that you are looking at, its expectation value. And we can see here that you have a sum of modes in that is related to the in modes and the other to the up modes. And what you can do is basically you can do it by hand. You remove the superradiant flux, and then you can work it out backwards, right? So you can look at the commutations relation and the modes that you need to define this thing to be like that. And it seems that you get not, I wouldn't say well-behaved state, but you get something that's only badly behaved in the horizon. So this is not as bad as you would expect. And so this quantities here are basically the expectation value of the current of the charged field, and you can see here that you can basically control the divergence by this power of f here, and the state is only badly behaved at the horizon, but we were already expecting that. And so yes, so this is the term that you have to add. So this, you can prove that it's an equilibrium state, so you don't have any fluxes, and you get the desirable property that it's as empty as possible at no infinity, but you also have a divergence on the horizon. And so we will talk a bit more about that in the conclusions, but so it appears that you can do it for the Reissner-Nordström case, which is not really the same that happens in the Kerr spacetime, but we are sure at some point that we will find a pathology in this state for something that we will talk about in conclusions. So we can also do it for the HHawkinslike state, which I'm calling HHawkinslike state, which basically you try to mimic the properties of the HHawkin and Schwarzschild. And in this case, you get something it's better to understand. So you get this cotangent, this hyperbolic cotangent term here. And this is just a fancy way of looking at that, because this is just a thermal factor, because the cotangent, the hyperbolic cotangent is, sorry if you cannot see, but it's hyperbolic cotangent minus 1 is basically just the thermal, the Bose-Einstein factor up to a multiple. And so basically what you do when you multiply the modes, the contributions of each mode to observable is basically, if you multiply it by this hyperbolic cotangent factor, you are actually considering a state that is thermally populated with particles in its set of definite quantum numbers. And you can, if we look at here, you can do it in several ways, because you can use as the thermal factors are omega over the temperature of the black hole, which is TH here. But you can also use the tilde omega, the omega tilde thing. But the HHawkin state is the one that you do it this way. So you thermalize all sets of, both sets of modes, and you also subtract the superradiant flux. And you get something that's very interesting at first, because when we were computing that, we were actually very happy with the first results, because this, for instance, is the scalar condensate. And you can see here that you have no divergence whatsoever. And if you look at this flux here, which basically the flux of this state minus the flux of the Bowler of the past Unruh state, you get something that's just the flux of the past Unruh state. So you get something that's actually, you don't have any fluxes. And so it appears everything is going well, because it appears it's an equilibrium state. And you can also look at the current, and both components of the current, of the scalar current. And you also, the only divergence you have is expected, because I don't think you can see it, but you have a u over minus 1 in here. And if we look at the Penrose diagram of Reissner-Nordström, u equals 0 is the future horizon. So this power of f here is actually only there because we are going to cancel this behavior of u going to 0. So it appears that everything is fine because you don't have any divergence up to now. But if you look at the stress energy tensor observable for the charged field, you get something like that, and this is bad because you need, basically what you need is 1 power of f to each power of u you have in this plot, and we can only multiply it by 1 power of f here. So this is in fact a sign that this quantum, this observable is divergent at the horizon. And of course, a similar result holds for the neutral scalar field in Kerr spacetime. So some final remarks is, so it appears that we can build a polar-like state that's regular outside the horizon and as empty as possible. But we expect that to have other pathologies because of what I'm going to say. So one thing that we can do is computation of renormalizable quantities, so especially the stress energy tensor. And the problem, why we expect other pathologies for the this Bowler-like state is because of this theorem here, which is the K-wall theorem, and also some theorems proved in another paper by Elizabeth that basically show that you cannot have this kind of things in Reissner-Nordström or in Kerr. So basically what happens that if you look at the superradiant modes that you have both in the Reissner-Nordström case and in the Kerr spacetime, it seems that you cannot, if you try to hide the fact that superradiance happens quantum mechanically, you get problems in other parts of your theory, and it appears that you cannot do that in this case. So one thing that's we can try to ask is if there are other ways to circumvent the K-wall theorem, which basically it says that there are no HHawkinslike states for Kerr spacetime, and there isn't actually a proof for the Reissner-Nordström case, but if you look at the K-wall theorem is as general as possible, so you don't expect you don't expect there will be a lot of changes for the Reissner-Nordström case, and this was actually said by Bernar-VIII himself when we showed it to him. But of course there isn't. I don't think there is a proof yet. And of course it's another perspective. So I would like to thank you for the attention, and that's it.
Thank you. Questions?
Hi, Rafael. Many thanks for your presentation. I'm not an expert in the field, so please don't judge. So when you were mentioning the Huru state, that's like the Rindler accelerated observer that is measuring a thermal radiation. It's that kind of Huru effect?
Not exactly, because one could argue that if you look at, for instance, for the Rindler state, right? So the Rindler state is different from the Minkowski state, right? So what happens in the Unruh effect is you have the Minkowski state, and it's seen for the Hindler observer, so the one that is undergoing uniform acceleration, he sees the Minkowski state as a thermal bath of particles. So you are looking at the same quantum state, the one that's very well behaved that you know from the usual flat space QFT. And actually the Reindler state is a different state that the Reindler observer sees no particle. So the Reindler state is actually, it's more similar to the Bowler state in Schwarzschild, because the Bowler state is the one that you define when you don't see any particles, according to this notion of positive frequency that you. Yeah. So yes, so these things make sense if you think about it, because the static observer is the one that defines the positive frequency modes with respect to the usual Schwarzschild time, and an static observer is similar to the Reindler observer, which is the one that undergoes uniform acceleration.
Okay, actually, this was just a curiosity because I didn't know that. Thank you. The question that I had was super radiance. You were mentioning super radiant modes. It actually doesn't really need an horizon. It just needs an ergo region.
Mm-hmm.
So everything that you talked about actually needs an horizon, as far as I understood. So could you have some of your effects in horizonless compact objects, for instance?
Yeah, I think Kyle asked this question 3 years ago, and we are still trying to figure it out. So we don't actually know if it's. So this is a nice question. It's a great question, but we don't actually know. So it seems from the construction, you need the horizon all the time, but at some point you can make the argument that the horizon doesn't really matter from a heuristic perspective, but we don't know how to build it in any case.
There are some papers on the solution, right? I think there are some papers by Otterwill that consider, instead of putting a horizon, I think he placed a surface there and found that parts of these effects are suppressed. I guess, if I'm remembering, this has been 3 years, he said. But yeah, but it's an interesting for rotating objects. Like instead of is those type of black hole mimickers, right?
Yeah. Well, more questions? I see. No. Online, perhaps. If not, let's thank the speaker again. Thank you.